gravitational potential energy, which we typically write as UG. I like doing the spring potential energy first because you could see that the spring gets distorted, it gets changed. So in this situation, what we want to do here is that we want to play sort of the same game of what actually happens here. So if I look at this guy, here's what we find. That there's very similar approaches between the spring and the gravitational potential energy. So suppose we lift a box from the surface.
Huh? I was gonna fucking pause the class, but I forgot it's live.
Hey, why don't you mute yourself?
It's because he's writing so fast, and I literally click it to pause. But
hey, do you mind muting yourself? Thank you. Suppose we lift a box from the surface of the earth above our heads. So what do we mean by that? Well, we have the surface of the earth right here. Okay, and we have to think about the earth. And I have a box right here. And our whole goal is to lift this box. So as I lift this box, what's actually happening? So if I look at what happens before, to what happens afterwards, you have lifted this box up. So I want to play the same game that I did with the spring. In this situation, I had an external force, which is the force of my hand. And what does it do? It pushes it up in this direction right here. And because of this, the force of my hand or the work of my hands does positive work. So I could come over here and I could just say that the work of my hand does positive work. And as a consequence, it changes the energy of the box. So again, what I'm really thinking about is that I'm thinking about this box. And it has this external forces acting on it. So now, if I look at this slightly different, at the same time, I actually have the force of gravity acting down. But the work done by gravity is not positive, it's also negative. And in a very similar situation, what we do here is that we focus only on gravity and not our hands. So what we do know here is that the work of our hands is positive, which implies there's an increase in energy in the box. So we know that has to be an increase. Now, with the focus on gravity, we could then say that the work of gravity here, that this quantity right here, this is a positive quantity. And as a consequence, it then changes the energy. And again, we play this game as before. Here, the box starts and ends at rest. Therefore, the kinetic energy change is zero. So we have no other thing to conclude here is that this is where the stored work goes. It goes into the potential energy in this situation. So now what we're doing here is that we can calculate this thing. Following the same type of thing here, then mathematically, we can calculate the work of gravity. And here's how we do it. Very similar to as before here. We have a box. And it's at rest relative to the ground here. And then what do? We lift the box up. So as I'm looking at these two states, as I'm lifting it up, I'm lifting it from a height of y1 to a height of y2. So if I look at this displacement with the force of gravity acting down, we could immediately say that the negative of the work of gravity, that this guy has to be the negative, and then we got to calculate gravity here. So if I make this my positive and this is my negative sign, then what happens here is that you can see here that the force of gravity here is automatically negative, and the distance that it travels here is going to be from a distance of y2, from y1 to y2 right here. And so if I start putting in the details here, the force of gravity, of course, is going to be mg. So then I'm going to get, so if I focus on this, you could see that that minus sign and that minus sign cancel out. So then I'm going to get a term that then reads mg times y2 minus mg times y1. And because this shows up so much, we then define this as the gravitational potential at 2 minus the gravitational potential at 1. And this is our change in gravitational potential. In other words, the work energy theorem states here that the work of gravity is equal to the change in gravitational potential, which is equal to UG2 minus UG1, and this is equal to mgy2 minus mgy1. And this is what the work energy theorem says. That the work done by gravity does not disappear, but reappears as stored work. And this stored work is what we call the gravitational potential energy. And that's what this delta U is right there. Now, I'm going to say here is that there's something that I did not talk about here. And you're going to see here is that there's this reference thing that we'll have to deal with. But by the way, again, this work is still the area, even though I didn't mention it this time because we could calculate the work quite easily here. What you're going to find here is that the work here, so the work is still the area. So if I was to plot the force, and then, let's say versus y, you could imagine that if I just look at the magnitude of this thing, the gravitational force, that value is a constant force near the surface of the Earth. And then if you look at this here, this is my height change right there. Let me be careful here. When I say mg, this value right here is mg, which is a constant. Maybe I should write it like this. And then if I write this as y1 and this is as y2, you could see that the area of this guy, right? The area is a rectangle. And so therefore, the area without the sign is then going to be mg times the difference of the height changes, which gives you exactly the same thing. So one of the trickiest things in this whole process here is that what actually is the reference points in potential energy. This can get really, really tricky. And what we say here is that the work energy theorem clearly defines only changes in energy as meaningful. Well, what that means here is that when I look at a potential energy term, you get a term that reads U2 minus U1. It turns out that this term right here, this is what they call the reference potential. And almost always, this reference potential is defined to be 0. So what we find here is that it's standard to define the reference potential to be 0 almost always. I could think of certain places like in electricity and magnetism not to choose it to be 0, but the vast, vast majority of the time, we choose it to be 0. So here's what we mean by this. So I'm going to give you an example, and it looks like this. So imagine that we're going to drop a ball onto a table. So we're going to drop a ball onto a table. And so here's what we find. I have a tabletop right here. And when I'm looking at this tabletop, we can define then our reference potential to be 0. So we want to pick our reference potential to be 0 at a convenient location here. Most people will define that y is equal to 0 at the floor. But you could imagine that if I drop a ball, let's say I start the ball here, and then it goes all the way up. It falls from here and it falls down in this direction like that. So if I look at this reference of setting y equal to 0, what does this mean? I'm going to say that the height of this guy is going to be y2, and then this height of the ball initially, I'm going to call this y1. So I'm calling this state 1 because that's where it starts, and I'm going to call this state 2. So what do I see in this? According to this, that if I calculate the potential in this case should be the difference between U2 minus U1. But according to our definition, this should be mgy2 minus mgy1. So if I look at this, this tells me then that I'm going to have mg of y2 minus 1. And if I define this as my height change, this height change is then going to be delta y, no matter what. So this will be mg delta y. Now, note delta y in this case is 0, is negative quantity because it's going down. So that's one way that we could calculate this. But let's say that I actually change my picture. So what I'm going to do here is that instead of setting y equal to 0 at the floor, let's choose y equal to 0 at the tabletop. So then when I look at this scenario, here's what I'm seeing here. I have the exact same situation as before, but now I am setting y equal to 0 at tabletop. So what you're finding here is that this height right here is definitely, I'll call this y1 prime, and then this is y2 prime. So when I look at the difference, this distance, I'm going to call delta y prime. So when I calculate this thing, here's what I find. That the change in gravitational potential is still U2 prime and U1 prime, and I'm still going to get mg y1 prime minus mg y2 prime. But note that y2 prime is set to be actually 0. So in this situation, we've already defined that y is equal to 0, which tells me that y2 prime should be exactly 0. And so this quantity then reads yg 1y prime. So when I look at the distance between falling from 1 to 2 when measured from the floor, we can only conclude that this guy has to be the exact same distance between these two, even though I picked y equal to 0 to be a different location here.
Is that because the height never changes?
The height level does
the
not,
ground.
that the fall of the ball does not change. The height change is the same no matter how you measure that height change.